you can see me. Hello, hi, I'm Jay. Of course, I'm on the side lab. I just do mainly physics and imaging stuff. In my undergrad, I used Chicago in physics. Started off in Nashville, like many people in physics do. Then I moved more to a medical physics type thing. And right now I'm doing a master's in biomedical engineering at Case. And a lot of it still interest in getting a PhD in physics afterwards. So that's kind of my trajectory. What I do here mainly is focusing on imaging metrics such as top-level data analysis and radiomics. So what this project was improving radiomic analysis with TDA. What our lab did with this one here, who previously worked with TDA, and found a quantification of the top-level data analysis, and he called that something the FOM score or the consistent homology score. And I wanted to take that score and use it in radiomics to essentially see which is better for survival prediction in non-small cell lung cancer. So what we did here, this graphic shows we obtained image data, which is just a bunch of CT scans from the TCIA. And we extracted all the radiomic features, so orientation, and then the FOM score was also extracted. So this is like shape features, texture features, intensity features of that sort. And then we selected the features. So this was like penalized regression, to see what features we wanted. And then we did analysis, survival analysis, getting the hazard ratios, and then finally selecting a model. We can answer the question to see which is better, which is worse, do they work better together, do they work better in certain stages, and these are questions that we're going to answer throughout this project. So next slide. So for this one, to basically run our prediction, we find that high FOM and high PC1 are akin to better survival. And what this looks like, so when we define high FOM, we think of high FOM as tumors that are non-fractionated. So if we find a tumor that we want to focus on the homology of it, we see a low FOM would be tumors that are like in pieces. So we have tumors that are like fractionated, non-homologous. These were akin to lower survival. And the same for high radiomics. So for patients inside of high radiomics, this would be for tumors that are more, round, more circular, not many cavities. So therefore, we can treat it better, more targeted therapy versus a tumor that in different pieces. So this showed us that FOM and high PC1 were both independently predictive of their own survival. So the next question was to see how they worked per stage. So we found out that FOM is strongest in early stages, so this is stage 1 and stage 2, and then radiomics predict stronger in stages 3A and 3B. So then we asked the question, is FOM distinct from radiomics? Is FOM telling us the same thing that radiomics is? If so, should we or should we not combine them in one model? So the first step to do was to see if each one can still be predictive in a multivariate analysis. This one only shows the FOM, but both FOM and PC1 were able to be predictive in a multivariate analysis. This is when I use all the comorbidities and all the patient information and combine them with just the one metric. So this one just shows FOM here, that has a ratio of 1.15. So that's something that we want to see as it being predictive along with all the other features at the same time. Next slide, please. So this is when we did the RLC analysis. We wanted to see if how much information FOM adds that radiomics does. The exact number isn't right here, but we found that radiomics explains up to 90% of the variance in the data, meaning that FOM can give us a little bit more information than the last 10%. So we wanted to focus on what that can do. So what we did here is we did a 4-model RLC thing where we combined just the model plus the clinical data, model plus the FOM, model plus the principal components, which is the radiomics, and model plus everything. And we found that the model that had the clinical data, the radiomic data, and the FOM data all together gave us the best outcome. So what does this give us the idea to propose? So if we integrate topology into radiomic pipelines, maybe we can get stronger biomarkers. For the future, I wanted to expand the data set. So this data set kind of suffered from not having race-coded data set and like a lower patient sample. So in the future, I want to expand the data set with more race-coded data or more patients. Include genomic and demographic data, and reduce bias and cancer disparities in cancer treatment. For the opportunity, so radiomics is known as not necessarily used in a clinic, but for research purposes, there's an opportunity for improved model robustness and personalized oncology tools. So what I want to use this for is apply this to different cancers. So I'm essentially applying this idea to liver cancer, and then just seeing what I can do with that. But that's pretty much what I do with the imaging here.